Today, I'll talk about 100G, 400G, 800G extended reach technologies, standards, and applications enabled by silicon photonics. It's well documented that optical technology these days are driven by top cloud operators such as Alibaba, Amazon, Facebook, Google, and Microsoft. Light Counting is forecasting demand from these top operators from today to 2026. This transition is occurring from 100G to 400G, 800G at an increasing pace. And if we're looking at the transition from 100G to 400G to 800G, one of the key enabler is the single lane 100G optics. We're transitioning from 100G DR4, FR4 to a 100G DR1, FR1. On the other hand, 400G is transitioning from FR8 to 400G FR4. This is the inside data center portion of the technology. If we look at the long reach side, the optics is transitioning from 100G LR4 to 100G LR1 and 400G LR8 to 400G LR4. And these are backed by IEEE 802.3 standards, and this is covered fairly wide range of applications from 500 meters, 2 kilometers, and 10 kilometers. On the other hand, if we look at the 5G mobile network, this is another new technology is now widely deployed in the industry and around the globe. The mobile networks tend to require longer reach optics, and extended reach going to be one of the key requirements. And we'll take a moment to define what the reach is. So-called DR, it's up to 500 meters, FR up to 2 kilometers, LR up to 10 kilometers, and ER, which is the topic of this discussion, represents extended reach, and this is up to 30 to 40 kilometers. And then there is also a so-called ZR, which is really covers the 80 kilometer and above. And I'm using this diagram to show an end-to-end optical networking from 5G end user radio antenna sites all the way throughout the optical networking through the front haul, middle haul, back haul, and then metro, and eventually will be connected to the large cloud operator data centers. And throughout this network, different data rates will be required and different distance required, but it's clear in the 5G networks, a higher speed at a longer distance, over 40 kilometers and 80 kilometers are required to support this extensive optical networking requirements. If we're looking at how to extend 100G per lane to extend the reach, there is a 100G lambda MSA have recent activity defined the single lane 100G ER1. This is allow us to extend the single lane 100G optical technology to 30 to 40 kilometer reach. There's several benefits for 100G ER1. First of all, this is really strongly leveraged on 100G PAM4 components and DSPs. They are developed for data center application at high volume. And by leveraging this, we also reduced the lane count by 75% from the legacy 100G ER4. This is will offer the benefits of lower cost, but also enable smaller optical modules, such as SFP5060D and SFP112. In addition, this is also support 100G serial host interface to match the switches and routers upgrades. In addition, this is also offers WDM for new 5G and cloud connections with single lane 100G optics. And in the bottom here, this is just to show how simplified 100GR1 is compared to 100GR4 or 100GR4 Lite, so to speak. And 100GR4 are going to require 4 sets of components. In addition, also require SOA, which is an expensive component. And 100GR4 Lite will require 4 sets of transmitters and receivers, including high modulation speed optics and including the APDs. To achieve the 100G per lane extended reach, one of the critical requirements is to meet the fiber chromatic dispersion tolerance. And the technical nuance here need to be paid attention to, since zero dispersion does not occur only at one single wavelength. As a matter of fact, it requires to handle fibers with zero dispersion in a range from 1300 to 1324 nanometers. And in the picture here, I'm showing the ITU G652 document, which is really reflecting a survey results from multiple fiber vendors to provide the min and max chromatic dispersion of their single mode fiber. And you can see the distribution of zero dispersion point in the O band is anywhere between 1300 to 1324-ish. So in the ITU standard, the dispersion range then is defined by taking the slope of the dispersion and then also consider the zero dispersion point. So you come up with this formula for minimum and maximum over the distance. The other important factor to consider is what is the dispersion tolerance at 53 gigabaud PAM4 modulation. Here we're just taking a typical EML type of transmitters widely used by the industry. And this is a presentation by Yu Xu from Huawei presented to IEEE 802.3 CU task force meetings. And this is showing with different chirp factors, which is actually very common in EML type of transmitter, the dispersion penalties over a range from -60 to +37. That's the range is acceptable with a reasonable amount of dispersion penalties, quantified here by a 2.7 dB as a tolerable range. And this is give us the framework to consider what kind of wavelength channels need to be considered to meet this compliance of dispersion tolerance. Now we are taking this graph to look at what the maximum dispersion and minimum dispersion within this range, what kind of wavelength range can be used in 40 kilometer SMM fiber. And here you can actually see by the red lines in the horizontal box, which indicating the dispersion range from -60 to +37, and then intercept with the maximum and minimum dispersion line supported by the ITU formula we just presented. And the intersection point is basically give you the wavelength range. If you're looking at the range between the min-max, this is actually will just give you a single wavelength range from basically 1308 to 1310 nanometers, allow you to stay within the dispersion tolerance range. And we discussed earlier about the EML, and recently there are actually newer technology is considered particularly developed for data centers, and these so-called Mach Zehnder modulators on silicon photonics can also be leveraged to support longer reach optics applications. In this example, we are showing a silicon photonics Mach Zehnder modulator developed by SiFotonics. And in the same picture, also showing a driver, a BiCMOS driver IC to match the silicon photonics PIC. And in this example, there's multiple Mach-Zehnder modulators, but we're just showing what is the dispersion penalties from such Mach-Zehnder modulators. And we can see here from -60 to +37, the dispersion penalties can be maintained below 1 dB. The other key componentry to technology to support extended reach optics is a high sensitivity receiver at a high baud rate. And we'll discuss how germanium silicon APD is a new technology can be leveraged on. And germanium silicon APD have gained a very broad market adoption from 25G plus applications recently for 5G front haul type of applications. There are several benefits. Germanium actually had a very broad absorption range from 800 nanometer to 1550 nanometer. And silicon itself has a superior avalanche gain noise properties. By combining germanium silicon with CMOS process, allow us to gain both competitive performance, but also competitive in cost. So in the last few years, over 10 billion device hours have been deployed for 25G plus germanium silicon APDs. And we are showing here the SiFotonics ramp-up curve for the last few years. And recently, we also developed a 53 gigabaud germanium silicon APD explicitly for 100G PAM4 applications. And here we are showing the red dots and lines, basically showing we can extend the sensitivity from the green, which is a pin diode. We can basically gain about 6 dB to extending from -10 to -16 dBm in optical power sensitivity. And here we actually show a actual transceiver developed with germanium silicon APD receivers. And we actually tested over 0 to 70 degrees C with 36 transceiver samples. And this is actually tested over 40 kilometer of single mode fiber. And you can see we can meet the 100G lambda MSA defined 100G ER1-40 requirement. And since we already achieved single lane optics going extended distance, we can now offer a so-called NWDM variant, which allow us to extend to multiple wavelengths since we already achieved single lane 100G. In this case, we can offer 8 wavelengths over a single fiber with 400 gigahertz channel spacing, and wavelengths range from 1295 to 1311 nanometers. This channel spacing compared to LAN-WDM is cut down by 50%, so going from 800 gigahertz to 400 gigahertz. This allows us to offer a low latency, low power, low cost application versus coherent. For application-wise, we can actually find good application in 5G front haul. This actually offers customer an option to have 4x100G upstream and 4x100G downstream over a single fiber. And there's sufficient link budget to support over 20 kilometer transmission with multiple add drop filters at our EU side. In addition, this 100G ER1 transceiver also offers extended temperature range for outside plant radio unit installation applications. And I'll move on to a new type of 400G extended reach. This is also supported by 100G lambda MSA. This is to extend the single 100G optics, single lane 100G optics to 400G reach over 30 kilometers. The benefit from offering such new 400G extended reach is, first of all, we again leverage on 4x100G PAM4 components, DSPs already developed for data centers. In this case, we reduced lane counts by 50% from 400G ER8. And this is much lower complexity and much lower cost versus coherent ZR type of optics. And this is also supports 100G serial host interface upgrades by switches and routers. And since we now already offer 100G ER1 and WDM, we can offer an additional benefit with the breakout applications. Here we describe a proposed channel wavelength. In order to meet the dispersion time range from -60-ish to +37-ish dispersion range, we basically need to choose the wavelengths within this dispersion tolerance range. So as a result, the proposed wavelength channels are from 1304 to 1311.05. And these channels happen to be with a 400 gigahertz channel spacing. And again, leverage on the LAN WDM channels already exist. We simply adding additional 2 channels in between LAN WDM and achieving a total of 4 channel optics with 400 gigahertz channel spacings by supporting the dispersion range within tolerance. And we can further extend the extended reach to 800G. In this case, we recently proposed 800G ER8 to IEEE beyond 400G study group. And this proposal, again, leverage on the specification already developed for the 100G and 400G extended reach, but now we need to confine the channel plan further reduce to 1302 nanometer to 1310 nanometer with 200 gigahertz channel spacing. However, to meet the extended reach applications in this case, considering the dispersion versus the wavelengths, we need to extend the negative dispersion to negative 85 picosecond per nanometers. And this new proposal is still under consideration by the IEEE Beyond 400G study group. Now we are looking at the extended reach solutions, compare the IMDD, NRZ, IMDD, PAM4, and coherent detections. We further map out the data rates in the bottom, and then vertical axes indicating what the transmission distance is. The dashed line basically indicating what the extended reach optics is confined to. And here we can basically see below 800G, most of the applications can be supported by IMDD, but going higher speed and longer distance, increasingly coherent detection will start to play key roles. And in particular, at 800G, the industry is now actively discussing where the boundary is between IMDD and PAM4, IMDD and coherent detections. And this could be one of the battlegrounds right now. The industry is currently under discussion. In this chart, we are showing what the IMDD pros and cons versus coherent detections. From modulation format, IMDD can be modulated with NRZ and PAM4, and coherent detection currently has several options, including QPSK, 8-QAM, 16-QAM, etc. Optical component complexity point of view, IMDD is a lot simpler and coherent detection is more complex. From receiver amplification technology point of view, IMDD can use APD, so-called avalanche photodiode, or you can use semiconductor optical amplification plus PIN. For coherent detection, we basically use optical local oscillator as an amplification. From dispersion tolerance point of view, IMDD is relatively limited. Coherent detection with a more powerful DSP is more scalable. And this is obviously leading to a simpler DSP for IMDD, but fairly complex DSP for coherent detections. From latency point of view, IMDD is much lower in latency, usually in the 100 nanosecond range, and coherent detection tend to use more complex full error correction and other processing, so the latency is much higher. Typically is 5 microseconds or up. And from power dissipation point of view, IMDD is much lower, and coherent detection is much higher. If you're looking at the bandwidth scalability technology point of view, IMDD tend to use increased baud rate and multiple optical channels. For coherent detection, it can use the combination of baud rate plus IQ modulation plus polarization mux, and then can also use multiple channels. From spectral WDM efficiency point of view, IMDD is much lower efficiency. Coherent detection, since you can use the IQ modulation and pole mux, you can actually achieve much higher spectral efficiency. And compared to cost, IMDD tend to have lower costs, and coherent detection tend to have higher costs. In summary, IMDD is simpler, lower latency, power costs, but with limited efficiency in reach and WDM. Coherent detection, on the other hand, is more complex, higher latency, higher power costs, but supports longer reach and more efficient WDM. I would like to also comment the importance of latency for 5G front haul. 5G, one of the key attributes for 5G is it supports the so-called URLLC. This is actually ultra reliable, low latency communications. This is actually require less than 50 microsecond front haul latency. URLLC supports remote surgery, smart transportation, factory automation, gaming, etc. These are the emerging new applications supported by 5G. In this case, we should also look at the fiber latency is around 5 microseconds per kilometer. So that means for 10 kilometers, the limitation already 50 microseconds. So optical transceivers should not add much more significant latency since the fiber latency already at 50 microseconds over 10 kilometers. And IMDD offers fairly low latency in the 100 nanosecond range, and coherent actually will require higher latency. So in this case, it becomes important for 5G front haul to choose a lower latency transceiver technology. For example, using the 100G PAM4 type of options rather than coherent options. And we know that earlier, germanium silicon APD is one of the key ingredients to support extended reach, at least up to 800G, from 25G, 100G, 200G, all the way up to 800G. And silicon photonics coherent technology can also be leveraged to support coherent type of applications. And in the longer distance, for example, ZR and ZR plus type of applications, coherent already are dominating the higher baud rate applications. And we anticipate to go further beyond 800G. The silicon photonics will also support coherent applications with shorter distance. For example, in the industry, we already started to discuss 10-kilometer type of applications with coherent technologies. In summary, we are looking at 100G to 800G extended reach solutions throughout the 5G to data center networks. And we already discussed 100G ER1 and WDM can support front haul applications with multiple wavelengths and multiple 100G over a reasonable distance for front haul. And we also discussed 100G ER1 can extend the distance up to 40 kilometers. And then 400G ER4 will be quite useful for connecting metro type of applications, for metro type of applications, and also for data center type of applications. And 800G is emerging, and the industry is still discussing, do we use PAM4 IMDD, or we started to use coherent for 40-kilometer type of extended reach applications. In general, there will be a mix of direct detection, IMDD type of applications, and then also coherent will start to become a very viable alternative technologies to cover 40-kilometer and up, including ER and ZR, when the data rate start to increase, going from 400G to 800G. Thank you.